morning friends, my name is Ruturaj and today we are going to start our first BEE chapter, that is DC circuits. Now what is DC circuit? So any circuit through which a direct current flows is DC circuit. So being first lecture, let us discuss about basic terms in this chapter. So first is current. It is the flow of electrons per unit time. Current is denoted by I. I is equal to Q upon T, where Q is the number of charge and T is the time. Unit of current is ampere. Next is electric potential. So electric potential is the capacity of body to perform work. It is denoted by V, and V is equal to W upon Q, where W is the work. SI unit of electric potential is volts. Next is resistance. So opposition offered by a substance to the flow of electric current is resistance. So आप सबको ये एक basic formula पता होगा, that is R is equal to rho L upon A, where rho is the coefficient of resistivity, L is length and A is the area. Unit of resistance is ohm. You may write all this. Okay friends, let us take an in-depth look in resistance. So first we will discuss Ohm's law. So simple output of Ohm's law is V is equal to I into R, where V is electric potential, I is current, which is direct current because we are in this chapter DC circuits. R is resistance. So now let's talk about equivalent resistance. I will rub this. Okay, equivalent resistance. So first let's take series combination. Consider a circuit in which there are two resistances attached in series combination. Let it be R1 and R2. So equivalent resistance, it will be Req is equal to R1 plus R2. Okay. So second is parallel combination. So let's consider again two resistances. Okay, this is my one resistance and this is my second one. Let it be R1 and this is R2. So R equivalent is equal to 1 R1 R2 upon R1 plus R2. Okay, this is a direct formula, you can remember this. Okay, so now let's discuss about voltage divider rule. I will write it. This rule is specially applicable for series circuit. Okay, so now let us consider a circuit. I will draw it here. A series circuit. This is my DC supply and there are two resistances. Okay, this is my R1, this is my R2. The supply voltage is V and let I be the current flowing in this circuit. Okay, so in series circuit, the current through R1 and R2 is constant. Current through R1 and R2 is constant. Okay, so now by Ohm's law, let us write V1 is equal to I into R1 and V2 is equal to I into R2, where V1 and V2 are the voltages across R1 and R2 respectively. So now what will be I? So by Ohm's law, I will be equal to source voltage upon equivalent resistance. Now, as we discussed, equivalent resistance for this circuit will be R1 plus R2. It will be V upon R1 plus R2. So let us substitute the value of I. So this is the final outcome. V is equal to V1 is equal to VR upon R1 plus R2. So this is the voltage across resistance R1. Likewise, V2 is equal to V R2 upon R1 plus R2. Okay, thank you. Okay, now let's talk about current division rule. This rule is applicable only for parallel DC circuits. So now let us consider a parallel circuit with two resistances connected to a DC source. Okay, so capital I is the current flowing through this main branch. V is my source voltage. Now in parallel circuit, the voltages across this terminal and this terminal is constant. What varies is the current, which is here. Let us consider I1 and here I2. Let this be R1 resistance and this be R2. Okay, so this is our circuit diagram. Now let us understand current divider rule. So you can remember direct result of this, which is I1 is equal to I R2 upon R1 plus R2. Okay, you can note it. I1 is equal to I into R2. This R2 is very important due to inverse proportionality, and likewise I2 is equal to I R1 upon R1 plus R2. Okay, you can remember this. Now let us discuss about ideal sources. So now there are two types of ideal sources. So first is ideal current source, and the second one is ideal voltage source. So So ideal current source is denoted by this symbol in a circuit, where this is my direction of current. Let it be 2 ampere. This is the magnitude. So now current will flow from this to this. Let us name it A, and this is my B. So current will flow from B to A. This is its direction. Okay. Now let's talk about ideal voltage source. So this is denoted by a battery symbol, where this is of considered 5 volts and direction is this, from B to A. Now there is a point which has to be noted in ideal current source. The resistance is considered taken to be infinite, and for ideal voltage source, the resistance is taken to be 0. Okay, so we will need both the sources when we solve sums. Now let us discuss about source transformation. Okay, so there are 4 cases of source transformation. Let us discuss the first one, that is case 1. Okay, so case 1 states that a voltage source with a series resistance to be converted in a current source with a parallel resistance. Okay, so let us discuss with an example. So consider a circuit in which there is a resistance and there is a parallel voltage source. So let the magnitude of this resistance be 5 ohm and the magnitude of the voltage source be 5 volts. Okay, so now we want to convert this into a circuit which will consist of a current source with a parallel resistance. Okay, so now let's name these terminals. This is my A terminal and this is my B terminal. Okay, so what is now, let us determine the direction of the current. So now voltage source has a direction B to A, so my current direction will be also from B to A. So let us mention it like this. Now talking about the magnitude, so we will determine the magnitude with the Ohm's law. So by Ohm's law, I will write it here. Okay, now what does the Ohm's law states? Current is equal to voltage upon resistance. So let us substitute the value 5 volts upon 5 ohm resistance. It answer turns out to be 1 ampere. So magnitude of this current is 1 ampere and the value of resistance will remain same. It is 5 ohm. So in this way we have converted a series resistance with a voltage source into a current source with a parallel resistance. So please note it down. Till then I will write the case 2. Okay, now let us discuss about the case 2 of this source transformation. So case 2 is exactly converse of what we have seen in case 1. So let us see what is in case 2. So an ideal current source to be ideal current source with a parallel resistance to be converted in a voltage source with a resistance in series. Okay, so now let us discuss with an example. So I will consider a circuit which will have a current. It is in upward direction of 10 amperes magnitude and it will be having a resistance parallel of magnitude 1 ohm. Okay, 1 ohm. Now let's name the terminals. This is my terminal B and this is my terminal A. Now we want to convert this circuit into an ideal voltage source. Okay, so as we discussed previously, the direction will be upwards because the current source direction is also upwards. So now I will draw it. So this is my terminal B and this is my terminal A and it will be having a series resistance. So now value of resistance will be constant, that will be 1 ampere ohm. And now what will be the value of ideal voltage? So let us calculate it by Ohm's law. Okay, so V is equal to current into resistance, which is equal to 10 into 1, which is 10 volts. Okay, so this is my magnitude of voltage. Now I will just write it here, 10 volts. So now in this way we converted the entire circuit into a circuit containing ideal voltage source with a series resistance. Okay, so please note it down. I will move on for the next case. Okay, so now let us discuss about case 3. So what does the case 3 states? So series ideal voltage can undergo a algebraic sum. Okay, so now let us discuss about this. So consider a circuit having resistance R1 which is in series with V1 volts, and this entire thing is in series with R2, okay, which is in series with another voltage source that this is R2 and this is V2, and one more resistance which is in series with V3, and this circuit is continuous. This is my R3 and this is my V3. So point to be noted is that V1, V2 are having same direction and V3 is having opposite direction. So we will consider this direction to be positive. So this can be converted in a circuit. It will be equivalent circuit. Okay. So this will be, we will consider it under R1. This will be my net voltage V, and this is my R2. This is my R3. Okay, let's complete the circuit. Okay, so now what will be the value of V? So V will be equal to V1 plus V2 minus V3. So now I will explain you why the sign of V3 is negative. So in the final diagram we have considered this as our main sign, and the sign of V3 is exactly opposite to it. So we will attach a minus sign to V3. Okay. So now let us, I will rub this, you may note this. Okay, now let us discuss about our case 4. Now what does the case 4 says? Any parallel, yeah, please note it, parallel current source can undergo an algebraic sum. Okay, so I will explain it with an example. So let us consider this one source I1. Next is this source which is in parallel, yeah, same direction, and this is my I3. Point to be noted is I3 is having an opposite direction, and this circuit continues further. So now I will just draw its equivalent circuit, which will contain only one ideal current source. Okay, so I will determine its initial direction to be downwards. Okay, this will be I. So now what will be the value of I? So I will be, now downward is my main direction, so I3 will have positive sign and I1 and I2 will have negative sign. So I3 minus I1 minus I2. Okay, I purposefully took this sign as downwards to explain you all. Please note it. Okay, now let us discuss about some few more things related to Kirchhoff's law. So first is node. Okay, so what is node? Node is a network in a network which is equipotential surface where two or more circuit elements combine. Now next is junction. So junction junction, it is a point in network where two or more circuit elements join. So at a first glance it seems that the junction and node are the same thing, but yes, there is a difference. A node is a point in a network which is equipotential, which has an equipotential surface. This is to be noted. This is the main difference between the node and junction. So all the junctions are nodes. I will just conclude it. All junctions are nodes, but all nodes aren't junction. Okay, please star mark this, a very important statement. Okay, so next is branches. I'll write it branch. Okay, so branch is a part of network is a part of network where part of network lying between two junctions. Next is loops. So any closed path in a network is loop. Next is mesh. So it is the most elementary form of loop. Okay, so real application of all these concepts will be understood in sums when we solve sums. Okay, so I will rub it all, you please note it. Okay, so now let's discuss about the final Kirchhoff law. So let's discuss the first law. So what is the first law? Kirchhoff's current law. Current law. It is also written as KCL. So what does this law states? The algebraic sums of a current meeting at a junction or the node in an electric circuit is 0. I will write it. Please repeat. The algebraic sum of currents meeting at a junction or node. As we discussed previously, junction and node are almost same, but still they have a minor difference of equipotential surface. Okay, is 0. So now let us consider point A. There are many wires connected to that point A. Let this be I1, this be I2. Now point to be noted is I3 has an opposite direction as that of I1 and I2. This is my I3, this is my I4, this is again my I5, again I changed my direction, and this is my I6. Okay, so now consider currents going away from point A to be positive. Okay, so by KCL, I1 plus I2 minus I3 minus I4 plus I5 minus I6 is 0. So this is the final result of Kirchhoff law. This has a huge application when we solve sums. Let's talk about the second one. Okay, I just forgot to write this. Second, Kirchhoff's voltage law. Which is KVL. Okay, so now what does this law states? It states that in any closed circuit. Now please comment what is meaning of closed circuit. We discussed it previously. All mesh the algebraic sum of all electromotive forces. What are electromotive forces? Those are EMFs. Electromotive forces and voltage drops is 0. Okay, let us understand this with an example. Okay, I am having a circuit. This is my resistance R1. R2 resistance. What is this? R1, and this is my R2. This is my V volts. This is the voltage drop. Okay. Now take the direction of current I to be clockwise. So by KVL law, V minus I R1 minus I R2 is 0. Why this minus sign? So now electromotive force about R2 will be minus I R2. It will be negative, and it will always oppose the voltage drop. And that of R1 will be I R1, which is a minus sign, minus I R1. So we have final this equation for this small circuit. Okay, so now let's end this lecture today. Please like, share and subscribe my channel. Thank you.